Have you ever wondered how oxygen in the air or carbon dioxide from your breath stays together as stable molecules? That's the magic of covalent bonding, a phenomenon that gives atoms by sharing electrons. Hello, students. Let's explore the fascinating concept of covalent bonds, where atoms don't donate or take, but share. So, covalent bonding is all about the mutual sharing of electron pairs between atoms, and it usually happens between two nonmetallic elements. These atoms have high electronegativities, meaning they don't easily give up electrons. Why do they share electrons? Simple, to become stable. Atoms want to achieve a noble gas configuration. By sharing, they fill up their outermost shells, achieving a stable octet or duplet configuration. Let's say two hydrogen atoms come close, each has one electron. If they share their electrons, both feel like they have two, mimicking the noble gas helium. That's a stable molecule of hydrogen gas, symbolically written as H2. So remember, covalent bonding is directional, strong, and purposeful, creating molecules that are stable and prevalent in everything from water to DNA. Now that we know atoms share electrons, the next question is, how many electrons do they share? Let's break it down. First, we have a single covalent bond where two atoms share one pair of electrons. Take hydrogen gas as an example. Each hydrogen atom shares one electron, creating a pair. We write it as H-H or H2 gas. Next, a double covalent bond involves sharing two electron pairs. Oxygen gas is a classic example. Each oxygen atom has 6 valence electrons and both share two pairs to complete their octets. The molecule is written as O equals O or O2 gas. And then there's the triple bond where atoms share 3 electron pairs. Like in nitrogen gas, each nitrogen shares 3 of its 5 valence electrons, forming a strong N triple bond N or N2 gas. Each of these bonds, single, double, or triple, differs in strength and length. Single bonds are the longest and weakest, while triple bonds are the shortest and strongest. You'll often see these in electron dot structures, which clearly show how many electrons are being shared. Look at the screen now for visual clarity. Alright, so far, we looked at bonding between similar atoms. But what about different ones? Can two dissimilar nonmetals form covalent bonds? Absolutely. Let's take the water molecule H2O. Here, each hydrogen shares one electron with oxygen, and oxygen shares one with each hydrogen, forming two single covalent bonds. The result? A bent molecule with partial charges giving water its polar nature. In ammonia, NH3, nitrogen forms 3 single covalent bonds with 3 hydrogen atoms. Nitrogen has 5 valence electrons and needs 3 more, so it shares with 3 hydrogens. The key here is, even with different atoms, sharing still happens. But because the atoms are not equally greedy for electrons, the shared pair can be pulled more towards one atom. This unequal sharing is what creates molecular polarity. We'll dive into that in a later scene. For now, remember, dissimilar atoms can and do form covalent molecules by sharing electrons strategically. Now let's clarify two important terms, covalent bond and covalent compound. A covalent bond is the chemical link that forms when two atoms mutually share electron pairs. It's like a handshake where each person contributes equally. But when multiple atoms are bonded like this, the result is a covalent compound. These are discrete molecules, not ions, and they're found everywhere, from methane in your gas stove to glucose in your food. Each covalent bond consists of one shared pair contributed by both atoms. Depending on the number of shared pairs, the bond can be single, double, or triple. For example, in methane, that's CH4, the carbon shares one electron with each of the four hydrogen atoms. So we have four single covalent bonds. Covalent bonds are strong, directional, and fundamental to molecular architecture, whether in simple gases or complex organic structures. Now let's talk about covalency, the bonding capacity of an atom. Covalency is the number of electron pairs an atom shares when forming covalent bonds. It depends on the number of electrons the atom needs to complete its outer shell. Carbon has 4 valence electrons. It needs 4 more, so its covalency is 4. In CH4, methane, carbon shares 1 electron each with 4 hydrogens. Oxygen has 6 valence electrons, so it needs 2 more. That gives it a covalency of 2, like in O2 gas. Nitrogen has 5 valence electrons, it needs 3 more, so its covalency is 3, as seen in N2 or NH3. Some atoms show variable covalency. Sulfur, for instance, can show 2, 4, or 6 depending on the compound. But most elements like hydrogen, oxygen, nitrogen, and carbon have fixed covalency in stable molecules. You'll often see these numbers reflected in electron dot structures where each shared pair is drawn as a line or pair of dots. Not all covalent bonds are the same, some are nonpolar and others are polar. Let's begin with nonpolar covalent compounds. When the atoms involved have equal or very similar electronegativities, they pull on the shared electrons equally. The electron cloud is evenly distributed. For example, in H2, Cl2, or O2, both atoms are identical, so there's no charge separation. The molecules are symmetrical and electrically neutral. But in polar covalent bonds, the electron sharing is unequal. One atom pulls harder on the electrons. Take HCl, hydrogen chloride. Chlorine is more electronegative than hydrogen, so the shared pair is closer to chlorine. This creates a partial negative charge on Cl and a partial positive charge on H. We write this as delta minus on Cl and delta plus on H. Same happens in H2O and NH3, giving these molecules a dipole moment and making them polar. Polar molecules tend to dissolve in water and show interesting behaviors like hydrogen bonding, a key force in biology and chemistry. So let's quickly recap everything we've learned about covalent bonding. We saw that covalent bonds form by mutual sharing of electron pairs, mostly between nonmetallic atoms. These shared pairs help atoms complete their outer shells, leading to molecular stability. We looked at different bond types, single, double, and triple, depending on how many pairs are shared. We explored how similar and dissimilar atoms form covalent compounds, from simple hydrogen gas to polar water molecules. We understood covalency as the number of shared electron pairs fixed for most elements like carbon and nitrogen. And we classified covalent compounds into nonpolar and polar based on the symmetry and electron distribution. Covalent bonding is everywhere, in the oxygen we breathe, the methane we cook with, and even in the structure of DNA. It's the language of molecular architecture. I hope this session helped you see how bonding is not just about atoms connecting, it's about nature's strategy to create everything stable and functional around us. In the next video, we shift gears and explore the structure of an electrovalent compound, magnesium chloride.